Hello students, welcome to the class. So in the previous class we had discussed regarding photoelectric effect. We have seen what is photoelectric effect. Yes, when light radiation of certain frequency strikes the metal surface, the electrons are ejected from the metal surface and that is called photoelectric effect, right? And even what are the observations made by Einstein through this, his photoelectric effect is also seen by us. Apart from that, we have also discussed the conclusions. Yeah. And here we have a slight explanation which we have already discussed, but I have to consider it. So let us see, glance it once again. Einstein in the year 1905 was able to give an explanation of different points of photoelectric effect using Planck's quantum theory as under. Photoelectrons are ejected only when the incident light has certain minimum frequency. Yes, we have discussed this. It is correct. Only when the frequency is minimum frequency, that is called threshold frequency, then only electrons get ejected. Otherwise, there is no photoelectric effect seen. Second point, on increasing the intensity of the light, what will happen? Will the number of photoelectrons ejected increase? Yes, more electrons are ejected, but the energies of the electrons are not altered, because when you increase the intensity of the light, number of photons will increase, due to which more number of electrons get ejected. But there is no point of frequency, therefore the energy of the electrons is not altered. And we have seen this notation, this equation. And the notation what we have seen is, when the frequency is more than threshold frequency. Yes, when the frequency is more than threshold frequency, the energy will be more than threshold energy, correct? The energy will be more than threshold energy. And when the energy is more than threshold energy, what happens? The extra energy, so energy will be more than threshold energy. So what happens there? The energy, total energy will be threshold energy plus extra energy comes out as kinetic energy. And we know that kinetic energy is half mv square, right? So this extra energy equation comes out like this. We have seen how to solve it. So h nu is equal to h nu naught plus half mv square. What is h nu naught? Threshold energy. When it is written like this, we call it as work function. We call it as work function, denoted like this, symbol like this, or you can write wo also, w naught also, plus half mv square. So this was what we had seen. Yes. Yes. Moving to the next one. Electromagnetic radiation. So far, what all we discussed in electromagnetic radiations, we took the main important concept that about the waves we have studied. The radiations are in the form of waves, right? Okay. So there is a dual behavior of electromagnetic radiation. The study proved that there is dual behavior. That means double nature. Yes, dual nature. Electromagnetic radiations, just now we have seen they behave as waves. From the study of light, and other electromagnetic radiation, from the study of light, scientists came to the conclusion that light and other electromagnetic radiations have got dual nature. These are wave nature, and which is the other nature? Particle nature. Now, how to understand wave nature and particle nature? Wave nature is understood by us because we see when these electromagnetic radiations travel, we see different wavelengths, right? Visible light is the best example where we can find all the wavelengths. So that is wave nature. Now, how to explain particle nature? Whenever radiation interacts with the matter, it displays particle-like properties, in constant contrast to wave-like properties. And where we find this example? In the example of interference and diffraction, which it exhibits when it propagates. Propagates means what? When it is moving in certain direction. Some microscopic particles like electrons also exhibit this wave particle duality, and we call it as dual nature of electromagnetic radiations. Dual nature of electromagnetic radiations. And we already have discussed these properties of electromagnetic radiations. What are those properties? In the form of wave nature we have discussed, right? These are the wave nature properties of electromagnetic radiations. It has energy and has no mass. It travels at the speed of light. It can even travel through the vacuum. So only the radiations which are coming from sun They pass through the space where there is complete vacuum. It also comes from atoms. See, the radiations also come from the atoms. We'll see how further. It travels in which motion? Wave motion. So it will have wave nature. It moves through space as bundles of energy, that is packets of energy called photons, which was being proposed by Planck. Each wave has a frequency which is related to energy. Yes, Planck's quantum theory says energy is directly proportional to the frequency. Higher the frequency, higher is the energy. Okay. Moving to the next concept, spectrum. The picture what I have shown here, yes, the picture what I have shown here, this picture what you're seeing, what is this? This is a spectrum of visible light. So I call it as visible electromagnetic spectrum. We have studied what is a spectrum. When all the wavelengths are being represented, when you have certain pattern, or I can say arrangement of wavelengths or frequencies, so arrangement of wavelength or frequencies in the increasing order or decreasing order, we call it as that particular pattern what we get, we call it as spectrum. Here this is a spectrum of visible light, 400 nanometer to 750 nanometer. So visible light has range 400 nanometer to 750 nanometers. Yeah, so this is the spectrum. Yes, and how actually we get it on the photographic plate, this is the answer. Like this we observe, and here it is quite very clear. Where is violet? This side is violet, wavelength is more, and here is red, wavelength is very less. So longest wavelength is for violet and shortest wavelength is for red, or low frequency is for violet, or high frequency is for red. Yes, you can see here wavelength. As wavelength decreases, the frequency increases, and as frequency increases, the energy also increases. So VIBGYOR falls in the range 400 to 700 or 750 nanometers. Yes, so let us try to understand, try to define this spectrum. Okay. When a ray of light is passed through a prism, see in the previous one of the video we have discussed, when all these radiations, when all these wavelengths are seen at a stretch, this appears as a white light. Yes, that's the reason the visible light which comes through the sun, it is white light, right? It doesn't, we cannot see colorful lights here, yes or no? When this ray of white light is passed through a prism, the wave of with shorter wavelength bends more than the one with longer wavelength. So shorter wavelength wave, which is the shorter wavelength wave? The shorter wavelength wave is red. Yes, it will bend more than the wave with longer wavelength. Since ordinary white light consists of waves with all the wavelengths in the visible range, a ray of white light is spread out into the series of colored bands, and that series of colored bands is called spectrum. The light of red color, which has longest wavelength, is deviated least, while the violet, which has shortest wavelength, is deviated the most. So how do we see it? It is like this. Yes, it is like this. So this is what? This is when a ray of light is passed through a prism. Can you see here? When it is passed through a prism, the light splits, and that when it is recorded on a photographic plate, it appears like this. So violet, largest wavelength, and red, here they have made, there is a slight mistake, students. Violet, the light red color which has shortest wavelength, is deviated least, and violet which has longest wavelength is deviated the most. Please make that correction. Yeah, is deviated the most. Yes, so this is the explanation. So when a ray of light is passed through a prism, so we have this splitting of light, you can call it as dispersion also, and here when you record it on a photographic plate, we will get a pattern, and that pattern is called what? It is called spectrum. It is called spectrum, which is observed here. It is called spectrum. Yes, so shortest wavelength 400 nanometers, and here longest wavelength sorry, last wavelength between which range our ray of our VIBGYOR falls from 400 nanometers to 655 nanometers. Yes. Now, there are two types of spectrums. There are types of spectrums. Yes. So, there are types of spectrum. So, what are the types of spectrum? One is emission spectrum. One is emission spectrum. And second one is absorption spectrum. Absorption spectrum. So one is emission spectrum and second one is absorption spectrum. Yes, under emission spectrum, we have again three types. Yes, we have continuous, we have band, and we have line. Band is not very common, but these three are very common. Under absorption also, we have three: continuous, band, and line. We will be studying only continuous and line spectrum. So I can say we will be studying under emission, continuous emission spectrum. Spectra, you can say spectra is plural, and line emission spectra. Spectra, and under this continuous absorption spectra and line absorption spectra. There are four types, types. Yes. So what we mean by emission spectrum? So emission spectrum of a element or a compound you can consider. It is the spectrum of frequencies of electromagnetic radiations emitted due to an atom making a transition from higher state to lower state. See here, whenever an atom, let me say this is state 1, let me introduce the states as n, and this is state 2. Suppose an atom, a particle, say electron, is present in this state and its actual state is this. So what does it do? It will jump from this higher state to lower state. How does it jump? Energies will be different. So when it is jumping from higher state to lower state, it will lose energy. That energy which comes out, we call it as emitted energy, correct? Yes, emitted energy. That emitted energy will have certain frequencies. When you take on a photo, take those frequencies on a photographic plate, what spectrum you get is what? Emission spectrum. It is emission spectrum. So when an atom or a molecule is making transition from higher energy state to lower energy state, the radiations, the energies with different frequencies are emitted. Those frequencies, when they are noted on a photographic plate, the pattern what we get is emission spectrum and it will be colored. It will be colored. Yes, each element's emission spectrum is unique. Like how we have fingerprints, like our fingerprints are very unique. Similarly, none of the fingerprints of the people around the world match with our fingerprint, right? Similarly, emission spectra of a particular element or an atom of that element are what? They are unique. Emission spectra is noticed when the radiations emitted from a source are passed through the prism and then received on the photographic plate. As same thing, whatever radiations are received from here, when the emitted radiations are there, whatever those emitted radiations are received, when they are taken on a photographic plate, you can say frequencies or you can say wavelengths. Doesn't make any difference. What pattern you get, we call it as emission spectrum. Then what is absorption spectrum? Absorption spectrum. Yes, absorption spectrum, when any radiation when white light is passed through the vapors of a substance and then the transmitted light is allowed to strike the prism. Now I just told you, suppose I am passing the white light through the prism. Yes, so white light gets scattered. Yes or no? This scattered light has different wavelengths or different frequencies, I can say. Different wavelengths or different frequencies. When I take it on a photographic plate, I will get different colors. I will get different colors pertaining to what? pertaining to different wavelengths. That is called emission spectrum. Yes. When this light is passed through the prism, not all the light gets emitted. Some of the light get absorbed, correct? Yes, and that gets transmitted. That absorbed light, when you pass it through the prism, you will get dark colors, black, completely black, just like your photograph. When you click a picture through a camera, a negative is created, right? That negative is your absorption spectrum. And when you treat it with a chemical, you will get your clear color picture. That color picture is your emission spectrum. Will there be any change in negative and color picture? No, it will be entirely same, right? So here, if I'm getting, let me say I'm getting this spectrum with nanometers, say 380 nanometer wavelength, 450 nanometer wavelength, and 600 nanometer wavelength. Just imagine, I'm getting here colored bands. For absorption spectrum, I will get dark bands at same wavelengths, 380, 400, 450, sorry, and 600. Understanding? So this is about absorption spectrum. Yes, the dark lines indicate that the radiations corresponding to them were absorbed by the substance from the white light. This spectrum is called absorption spectrum. Dark lines appear exactly at the same position where the lines of emission spectra appear. That lines represent what? Wavelengths. It is an electromagnetic spectrum in which a decrease in intensity of the radiation at specific wavelength or range of wavelengths characteristic of an absorbing substance is manifested especially as a pattern of dark lines or bands. Dark lines or bands, you can see here. So this is emission spectrum and this is absorption spectrum. Yes, here emission spectrum is observed. Yeah, it should come as emission and absorption. Okay, take it like this. Yes, absorption line spectrum, emission line spectrum. Yes, absorption will be in colored form and emission will be in dark form. Yes, I just made a vice versa I told. Absorption will be in the colored form and emission will be in the dark form. Yes, differences between absorption spectrum and emission spectrum. An absorption spectrum can be defined as spectrum obtained by transmitting electromagnetic radiations through a substance. An emission spectrum can be defined as the spectrum of the electromagnetic radiation emitted by the substance. When absorption spectrum is produced? When it is produced when atoms absorb energy. And when emission spectrum is produced? It is produced when atoms emit energy. That means give energy. Absorption spectrum shows dark lines or gaps. Emission spectrum shows colored lines. Please don't follow these slides, students. It is, I don't know what mistake is being done here. It should come here. What I had told is correct, yeah? What I had suggested is right actually. This is emission spectrum, absorption spectrum. While making the slide, there might be some misconception by me. This is emission spectrum. Yeah, I've made it clear. So absorption spectrum will be dark lines. And you can see these colored bands. And the emission spectrum, colored bands. Yes. Okay. Shows dark lines or gaps, shows colored lines or gaps. An atom obtains a higher energy level when an absorption spectrum is given by that atom. And emission spectrum is given when excited atom obtains a lower energy level. What does emission spectrum accounts for? It accounts for wavelengths absorbed by the substance, and this accounts for wavelengths emitted by the substance. Emitted by the substance. Yes. Under this emission and absorption spectrum, we have, as I said, we have three types. Yes, we have three types, out of which we'll be studying two types. The two types are, one is continuous spectrum and another one is line spectrum. Now see, when you see a rainbow, rainbow appears like this. Yes, rainbow appears the same, right? This same it appears. So rainbow appears how? These are colors means what? They are pertaining to different wavelengths. And these wavelengths, are they not overlapping with each other? Yes or no? They are merging into one another. There is no gap between these colors. Yes. So when all the range, why do we get such overlapping? We get such overlapping when all the wavelengths are being shown. When all the wavelengths are being shown, we get these gaps. Even you can see here, better way. When all the wavelengths are being shown, we get a continuous band. We get continuous, all the colors will be merging into one another. All the colors will be merging into one another. Such a spectrum which shows certain range of wavelengths which are merging into one another, we call it as continuous spectrum. When a ray of light is analyzed by passing through a prism, it is observed that it splits up into 7 different wide bands of colors from violet to red like a rainbow. These colors are continuous, or you can say they merge into one another, so that each of them merges into the next. Hence, the spectrum is called continuous spectrum. Yes. Example for continuous spectrum is your rainbow, or when the white light is passed through a prism, what VIBGYOR we get is a continuous spectrum, right? Then what is line spectrum? Yes, line spectrum. When the vapors of some volatile substance are allowed to fall on the flame or Bunsen burner and then analyzed with the help of spectroscope, some specific colored lines appear on the photographic plate, which are different for different substances. For example, sodium or its salts emit yellow light, while potassium or its salts give violet light. That means when you see a spectrum, you will, suppose you have seen this spectrum, you will not get the colors continuous. In fact, you will get colors only at certain points. Say at this point I've got this color, at this point I'll get this color, at other point I'm going to get this color. Yes, I will not get range. There is discrete lines, very sharp lines are obtained, very narrow sharp lines are obtained. So this spectrum tells us what? It tells us about wavelengths only at certain ranges, only at certain fixed wavelengths are being told. Whereas continuous spectrum, all the wavelengths are being told. Yes or no? All the wavelengths are being shown. From range, you mentioned 380 nanometer to 600 nanometer, all the wavelengths will be shown. Therefore, all the colors will merge into one another. But here, at particular lines, sodium, if you see, you can find two lines at 589 nanometer and 590 nanometer something. Yes. So those lines represent what? They represent discrete, narrow wavelengths. And such spectrum is called what? It is called line spectrum. It is called line spectrum. So continuous versus line spectrum. Continuous spectrum is superimposed image of both absorption and emission, whereas line spectrum is either an absorption spectrum or an emission spectrum. It contains no observable gaps. There are huge gaps between the lines. Contains all wavelengths of a given range, and here it contains only few wavelengths. Rainbow black body radiations are the examples of continuous spectrum. Emission spectra of hydrogen and absorption spectra of hydrogen are the examples for emission spectrum. The main difference between continuous spectrum and line spectrum, what is the main difference? It is that line spectra can be seen as either isolated emission lines or absorption lines. Separate lines you can observe for line spectrum with huge gaps in between. Whereas continuous spectra do not contain gaps and can be produced and by superimposing the emission and absorption spectra of the same. Emission and absorption spectra of the same. Yes. So this is the difference between emission and absorption spectra, and we have seen what is emission and absorption spectra. Coming with the same understanding, let us try to understand what is line spectrum of hydrogen. Line spectrum of hydrogen. When electric discharge is passed through hydrogen gas enclosed in the discharge tube under low pressure, and emitted light is analyzed by the spectroscope. So here what is done, an experiment is taken to understand line spectrum of hydrogen. Now you may say, why hydrogen atom? Because hydrogen atom is the lightest atom. Lightest atom. It contains only one proton or only one electron. It does not have any neutron also, yes or no? Therefore, we consider line spectrum of hydrogen. Okay, fine. So what experiment is done is, this is a discharge tube which is taken. Into this discharge tube, hydrogen gas is taken, and you know that hydrogen gas is H2 molecules. Under low pressure and high voltage, these H2 molecules break into hydrogen atoms. H2 molecules break into hydrogen atoms. Yes. These hydrogen atoms, what happens? You know that hydrogen atom has got electrons. Yes. So electron, what happens when you apply high voltage? It will acquire energy. The electron gains energy. When it gains energy, it will move from lower energy level to higher energy level. It will move from lower energy level to higher energy level, from this state to this state. When this electron comes to this state, this is not the perfect house of that electron. This is the state orbit of that electron. So what this electron does, it will try to come back to its normal state. When it is trying to come back to its normal state, how it will come? It should give out that energy. It should release that energy which it has gained. Then only it will come to normal state. When it is releasing the energy, it releases the energy in the form of radiations. It releases the energy in the form of radiations. Yes, they are released in the form of radiations. And those radiations will have different wavelengths or different frequencies, right? When those wavelengths or radiation frequencies are passed through the prism and detected on the detector, that is a photographic plate, you will get a spectrum. And that spectrum is called line spectrum of hydrogen. Why line spectrum? Atomic spectra are all line spectra. Remember, whatever atomic spectra we have, all of them are line spectra. Yes. So this is the experiment. So these radiations are passed through the slit, made to fall on the prism so that they can scatter, and they are detected on the detector, that is the photographic plate. This is the spectrum obtained. When the spectrum is analyzed, they found that the hydrogen line spectrum, it contained few lines that is pertaining to certain wavelengths: 410 nanometer, 434 nanometer, 486, 456. So is it that the hydrogen spectra has got only 4 lines? These were only visible because these range fall between what? See there, 410 nanometer to 656 nanometer. There were 4 lines obtained. And this is a visible range, correct or no? So since it is in the visible range, human eye could detect only these 4 lines. What if we don't know whether there are some lines which are falling in infrared radiation and some lines in ultraviolet, because besides are these two radiations, right? Regions. Only in the visible range, which of them fell, they were visible to the eyes. And those were the first set of rays which were visible. And those rays were called Balmer rays or Balmer series, first series which were detected. Understanding? So this is the experiment which was conducted to understand the line spectrum of hydrogen. So discharge at very high voltage, hydrogen, what happened? The hydrogen gas, it dissociated into hydrogen atoms, and in the hydrogen atom there is electron. It jumped by acquiring energy, by gaining energy, you can say. It jumped to higher energy level, and there it was unstable. If you go to some other's place, some relative's place, you won't be comfortable there, right? You will be unstable there. When you come back to your home, you feel comfortable, you'll be stable. Same with electrons. Electron is present in its house. Because of gaining energy, it has jumped to higher energy level. It is unstable, so it will try to come back to its ground energy level. We call it as ground energy level, to attain stability. When it is coming to its ground state, it emits radiations. This radiant energy, here you can see, it is passed through the slit, made to fall on the prism, and all the wavelengths get dispersed. They get dispersed on the detector or the photographic plate, and that is called line spectrum of hydrogen. And it was found that it was having 4 lines, few lines at certain wavelengths, and those wavelengths were recorded. And those wavelengths were luckily found in visible region, because human eye can detect only the wavelengths pertaining to visible region. This made the scientists to think whether are there some any other radiations, because on one side of the visible region there is IR region, and on the other side there is ultraviolet region. Yes or no? So if there are any other rays falling in UV lines coming in UV region and IR region, that led to the further discussions regarding line spectrum of hydrogen. And the explanation was very well given by Rydberg. So on the basis of experimental observations, Johannes Rydberg noted that all series of hydrogen spectrum could be described in the following expression. So he gave the expression for it. nu bar, that is wave number, is equal to 109,677, 1,09,677. This is called Rydberg constant, 1 by n1 square minus 1 by n2 square per centimeter, where n1 is 1, 2, and n2 starts from n1 plus 1, that is next. If n1 is 1, n2 starts from 2, 3, 4. If n1 is 2, n2 starts from 3, 4, 5. These were the series. And this value is called as Rydberg constant for hydrogen. These were the series. For the first time, this series was observed by Balmer, which was found in visible region. 4 rays were seen. 4 lines were seen. And therefore, it was called Balmer series. First Balmer series was discovered. Then slowly they came up with the next remaining series. So Lyman series is found in ultraviolet region. Passion, it is found in near IR. Yes, because near to visible region is called near IR. This is middle IR and this is far IR. Yes, so this was the explanation. So let us see how the line spectrum of hydrogen was. Rydberg in 1890 has given a simple theoretical equation for calculation of wavelengths and wave numbers of spectral lines in different series of hydrogen spectrum. That is called Rydberg formula. What does Rydberg formula says? Nu bar, that is wave number, is related how to wavelength? 1 by lambda, correct? Is equal to RH, which is Rydberg constant, 1 by n1 square minus 1 by n2 square, where n1 will be lower energy level. If n1 is 1, n2 starts from 2. If n1 is 2, n2 starts from 3. This relation is valid for hydrogen atom only. Yes, if you have other species, then there is one additional term, that is Z square. What does Z stands for? It stands for atomic numbers. It stands for atomic numbers, right? So where Z is the atomic number of the species, here RH is constant, which it is called Rydberg constant for hydrogen, and the value of Rydberg constant is, you can write it as 109,737 or 1.09737 into 10 raised to 7 per meters. 10 raised to 7 per meter. So that is Rydberg constant. Rydberg constant, there are different values. This value what you are seeing, that is 1.09737 into 10 raised to 7 per meters. This is the value when wave number comes into consideration. Yeah, wave number comes into consideration. Okay, so and n1 and n2 are integers, and n2 is always greater than n1. N2 is always greater than n1. Yes, for any particular series, the value of n1 is constant. That means you should be knowing this. There are 5 series: Lyman series, Balmer series, Passion series, Brackett series, and Fund series. The value of n1 is constant and n2 depends on n1. Like here for Lyman series, n1 is 1, n2 is 2, 3, 4, and so on. It varies. I'll show you the image, the diagram also. For Balmer series, n1 is 2 and n2 varies from 3, 4, 5. Passion, n1 is 3, n2 varies from 4, 5, 6. Bracket, n1 is 4, n2 varies from 5, 6, 7. Fund series, n1 is 5, n2 varies from 6, 7, 8. So by substituting the values of n1 and n2 in that above equation, in this equation, wavelengths and wave numbers of different spectral lines can be calculated. If when n1 is 2, the expression given above is called Balmer's formula, because the series are pertaining to Balmer series. So let us try to understand all these series in a detailed manner. Lyman series, n1 is what? It is 1. The series was discovered during the years 1906 to 1914 by Lyman. Thus, it is named after him. According to Bohr's model, Lyman series is displayed when electron transition takes place from higher energy states, that is, higher energy states are represented as 2, 3, 4, 5, to first energy state. All the wavelengths of Lyman series fall in ultraviolet band. Yes. Balmer series, N1 is 2. This series was observed during the years 1885. See, for the first was Balmer, then came Lyman. Look at the years. By Johann Balmer. Thus, the series is named after him. Balmer series is displayed when the electron transition takes place from higher energy states 3, 4, 5, 6, 7 infinite to N1 is equal to second energy state. All the wavelengths of Balmer series, they fall in the visible part. Lyman series, ultraviolet. Balmer series, visible part of the electromagnetic spectrum. That is between 400 nanometer to 750 nanometer. In astronomy, the presence of hydrogen is detected by using hydrogen alpha line of Balmer series. It is also the part of solar system. Passion series, N1 is 3. The series was first observed during the years 1908 by German physicist Friedrich Paschen. Thus, the series is named after him. Paschen series is displayed when electron transition takes place from higher energy states, that is 4, 5, 6, 7, 8, and so on, to the third energy state. So, N1 is 3. All the wavelengths of Paschen series fall in near infrared region of the electromagnetic spectrum. The shortest wavelength of the next series, that is bracket series, they overlap with Paschen. Next series onwards, no, all the subsequent series, they go on overlapping. Very clear distinct lines are seen for Lyman and Balmer. Yes, from Paschen onwards, the series spectral lines, those lines are called spectral lines, they overlap. Bracket series N1 is 4. The series was first observed during the years 1922 by an American physicist, Frederick Sumner Brackett. Thus, the series is named after him. Bracket series is displayed when electron transition takes place from higher energy states, that is 5, 6, 7, 8, and so on, to the N1 equal to 4, that is fourth energy state. All the wavelengths of bracket series fall in middle IR region, infrared region of the electromagnetic spectrum. Fund series N1 is 5. It was observed during the years 1924 by August Hermann Fund. Thus, the series is named after him. Fund series is displayed when the electron transition takes place from higher energy states, that is 6, 7, 8, 9, 10 to fifth energy state. So, N1 is 5. All the wavelengths of Fund series fall in far infrared region of the electromagnetic spectrum. Yes, we know only these series, but there was one more which was discovered in the late years of 1950s, and that was Humphrey series, where N1 is 6. This series was observed during the years 1953 by an American physicist, Curtis Humphreys. Thus, the series is named after him. Humphrey series is displayed when electron transition takes place from higher energy states 7, 8, 9, 10, 11, and so on to the sixth energy state. All the wavelengths of Humphrey series fall in far infrared region. So Lyman series comes in ultraviolet, Balmer series comes in visible part, remaining all Paschen, Brackett, Fund, and Humphrey series, they all are overlapping with each other, not very strongly, but they show slight overlapping spectral lines, and they all are falling under infrared region. Here is the line spectrum of hydrogen. The line spectrum of hydrogen, you can see here. So this is Lyman series observed under ultraviolet region, Balmer series observed under visible light, Paschen, Fund, Brackett, and here comes your Humphrey series. Humphrey. Yes, all of them are seen in infrared region. Yes, all of them are seen in infrared region. So see Lyman series. From all, this is second energy level, third, fourth, fifth, sixth, seventh, eighth, and so on up to infinity. To which energy level? First. So N1 is 1 and N2 varies from here. Balmer, it starts from 2. So N1 is 2. Then third, fourth, fifth, sixth, seventh, eighth, and so on up to infinity. Paschen, N1 is 3. See here, it is 3. Brackett, N1 is 4. And Fund series, N1 is 5. Yes, so lower energy levels are being mentioned. This is the energies of those energy levels. When we discuss about Bohr's model in detail, we'll come to know about these energies, right? Okay, so Bohr's model of an atom. Niels Bohr, he has given a very wide contribution to the field of atomic theory. Bohr's model of an atom was proposed by Niels Bohr in 1915. It came into existence with the modification of Rutherford's model. It came into existence with the modification of Rutherford's model of the atom. When Rutherford's model had got certain limitations, and we already know what are the limitations. That is, when accelerated electron will go on losing energy, what happens? It will fall. Eventually, it will fall into the nucleus. Yeah, that was the instability of the atom, which was not explained. So Rutherford's model introduced nuclear model of an atom. Yes, in which he explained that nucleus positively charged is surrounded by negatively charged electrons. So Rutherford, he was successful in telling us that electron is something like this, and there is a nucleus which is positively charged, and this nucleus is surrounded by negatively charged electrons. So they are moving in certain paths, and those paths are called orbits. But he could not explain the distribution of the electrons in those orbits. Like in this orbit, how many electrons will be there? Is there only one orbit where the electrons are revolving, or there are many orbits in the atom? That all things were not explained by Rutherford, right? Bohr modified this atomic structure model by explaining that electrons move in fixed orbitals called shells and not anywhere in between. And he also explained that each orbit has fixed energy. Each orbit has fixed energy. Rutherford basically explained that nucleus of an atom, and Bohr modified that model into electrons and their energy levels. Bohr's model of an atom was proposed by Niels Bohr in 1915. It came into existence. Okay, there is repetition. So he modified, yes, there is repetition in the concept what we have discussed. Yes, so positively charged. So what he said, Rutherford basically explained that nucleus of an atom, and Bohr modified that model into electrons and their energy levels. Bohr's model consists of what? Small nucleus, which is positively charged, surrounded by negatively electrons moving around the nucleus in the orbits. Bohr found that an electron located away from the nucleus has more energy. Yes, the electron which is located away from the nucleus has got more energy. So he said, suppose if this is, yeah, so if this is the nucleus, yes, so the electron which is located far away from the nucleus has more energy, and the electron close to the nucleus has less energy. That means as you move away from the nucleus, the orbits will go on having increasing energy. The energy goes on increasing. So E1 will have less energy than E2, which has less energy than E3. Yes, this was said by Bohr. Yes, this is a slight introduction for Bohr's model. Bohr gave his explanation in the form of postulates. What it says, in an atom, electrons, what are electrons? Negatively charged particles. They revolve around the positively charged nucleus in certain definite circular paths called orbits or shells. Each orbit or shell has fixed energy, and these circular orbits are known as orbital shells. The energy levels are represented by an integer n equal to 1, 2, 3, which are also known as quantum number, principal quantum number. This range of quantum numbers starts from nucleus side with n equal to 1, having the lowest energy level. The orbits n equal to 1, 2, 3, 4 are assigned as KLMN shells. And when electron attains the lowest energy level, it is said to be in the ground state. The electrons in an atom move from lower energy level to higher energy level by gaining required energy, and electrons move from higher energy level to lower energy level by losing energy. Okay, so let us try to understand all these points. Okay, fine. So what this theory says? So here, okay, let me say I'm drawing the, okay, a small, let us say I'm representing the electrons. I was trying to put a picture for Bohr's model. Okay. Okay, so let us say this is the nucleus. And these are what? Where the electrons are traveling, where the electrons are revolving. The electrons are what Bohr said is, the electrons are revolving. First point, what he said, an atom consists of positively charged nucleus. So an atom consists of positively charged nucleus. This is said by Rutherford also, which is present at the center of an atom. Okay, and it is responsible for entire mass of an atom. So this nucleus is responsible for entire mass of an atom. Second point, the electrons revolve around the nucleus in certain permitted circular orbits. In certain permitted circular orbits of definite radii. So these are the orbits and this is the radius, right? Certain different radii, the electrons are revolving around the nucleus in these particular areas, and those are called as what? Orbits. These are called orbits, correct? They are called as orbits where electrons are revolving. The permitted orbits are those whose angular momentum of an electron is integral multiple of h upon 2 pi. Yes, angular momentum. What is momentum? Mass into velocity. Momentum is mass into velocity. Angular momentum comes when we speak about circular. So this is all circular orbits, right? So angular momentum is equal to h upon 2 pi. They are saying it is equal to integral multiples, nh upon 2 pi. nh is Planck's constant, n is the number, whole number, mass of electron, velocity of the electron, and radius of the orbit in which electron is present. When that particular electron obeys this law, mvr is equal to nh upon 2 pi, then that will be the allowed orbit. And n is what? 1. If it is obeying, this electron is obeying this law where n is 1, then that electron can be allowed in first orbit. If n is equal to 2 and that electron is particularly obeying, then it will be that will be allowed. That will be the house of that electron. Yes, you can see like that. Okay. Yes. So this is what MVR, it is the angular momentum. Yes. And therefore this rule we call it as principal quantization, Bohr's quantization postulate. I call it as Bohr's quantization postulate. Then can the electron, until further what he said, very important point what he said, until and unless the electron is revolving in its permitted orbit, or you can say in its allowed orbit, it will neither lose energy nor gain energy. So this was the overcome of Rutherford's limitation. So what Rutherford's limitation was, when it is continuously revolving, accelerating, it should lose energy and fall into the nucleus. But what Bohr said, until and unless that electron is in its own allowed orbit, permitted orbit, it will neither lose energy nor gain energy. That means for that electron, the energy remains fixed. Energy remains fixed for that particular orbit. For that particular orbit, the energy is fixed. That's the reason the orbits are also called energy levels. And they are denoted by the symbol N. where n stands for principal quantum number. Quantum number. Principal quantum number. And this n is denoted like this. N is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, and so on. So this is n equal to 1. This is n equal to 2, n equal to 3, n equal to 4. These are called energy levels, and they are denoted as capital K, L, M, N, shells also. You can call them shells also. Yes, you can call them shells also. Understanding? So why they are called as energy levels? Until and unless that electron is revolving in its own orbit, it will neither radiate energy, that is lose energy, nor gain energy. So energy of that orbit, the electron's energy remains fixed. Therefore, the orbits are also called as energy levels, denoted by the symbol small n. Small n stands for principal quantum number. N starts from 1 near to the nucleus, and it is denoted as 1, 2, 3 or KLMN shells. Yes, KLMN shells. Now, see, what if, yes, I take another constant here. So this is my atom. Okay. Okay. So let me say this is the nucleus. Okay. And what is this? Let me represent it with something else. N is equal to 1, n is equal to 2, n is equal to 3, or I can say K shell, L shell, M shell. So energy levels there. Now see, let me say there is an electron here. So here, this is the electron. That means it is allowed orbit for this electron. Why it is allowed? Because this electron is particularly obeying this law. MVR is equal to NH upon 2 pi. And here there is one electron. So the second orbit is the allowed orbit for this electron. And let me say here also there is one electron. So there will be different electrons. I am taking one example in each orbit. Okay. Until and unless this electron is revolving in its own orbit, its energy remains same. Same condition for here. Until and unless this electron is revolving in its own orbit, its energy remains same. And same condition applies here also. And this energy, as you move from the nucleus, energy goes on increasing. So first energy level will have lesser energy compared to second. Second will have lesser energy compared to third. Yes, this is the understanding. Okay, we will see. Bohr has given the expressions also for calculation of energy, for the calculation of the radius, this radius of the orbits. Yes, everything. Velocity of the electron with which it is moving, everything. Now, suppose from somewhere, from external source, what I will do is, from the external source, I will give energy to this electron. When I give energy to this electron, this energy, what it will do, this electron, what it will do, this electron will gain energy. Yes. When it gains energy, the energy of this particular orbit is fixed. When it is gaining extra energy, will it remain in this shell? No, it will, what it will do, it will jump to higher energy level. So when electron gains energy, it jumps from lower energy level to higher energy level. Yes. So here, what I'm trying to say here is, let me make this point very clear. Yes. When electron gains energy, or you can say when electron absorbs energy, what happens? It jumps from lower energy level to higher energy level. Yes, it is jumping from lower energy level to higher energy level. This energy level for this electron is called ground energy level. Ground energy level, or you can say ground state. For this particular electron, this is the ground state. For this particular electron, this is the ground state. Yes. So it jumps from lower energy level to higher energy level. And this process is called excitation. What it is called? It is called excitation. When electron jumps from lower energy level to higher energy level, When it absorbs certain energy, it jumps from lower energy level to higher energy level, and that is called excitation. And that higher energy level is called excited state. What it is called? Excited state. And excited state will be always unstable for the electron, because this electron, it should have this particular amount of energy. But what this electron is doing, it is gaining energy and jumping to this state. So for that electron, that excess energy becomes more. Yes, therefore it becomes unstable. And nothing in this universe tries to remain unstable. Everything tries to attain stability. So what does that electron do? It has jumped here now by acquiring energy. So this has become excited electron. Electron gets excited, we say. Electron gets excited and comes into excited state. Now that electron is not good in that state. It wants to come back to its normal ground state. So what it does? That particular electron loses, or you can say radiates that extra energy. Radiates that extra energy. Then it will jump from higher energy level or excited state to lower energy level, or I can say excited state to ground state. Yes or no? Higher energy level to lower energy level. This process is called transition. This process is called transition. So this electron is not stable here. Therefore, it will jump from higher energy state to lower energy state. When it can jump? When it gives out excess energy in the form of radiation. Excess energy in the form of radiation. And what is this process called? It is called as transition. It is called as transition. Understood? It is called as transition. Did you get my point? So these two things happen. What Bohr explained. So what Bohr explained? He explained first point. What did he say? An atom consists of positively charged nucleus, and that is responsible for the entire mass of an atom. Yes. The electrons, and this was also said by Rutherford also, at the center it is present. The electrons being negatively charged, they revolve around the nucleus in certain permitted circular orbits called shells. You can call them orbits, you can call them shells. Third point, how those electrons are having, say, these orbits only. So only those orbits are allowed for electrons whose angular momentum. And how do we denote angular momentum? MVR is equal to NH upon 2 pi, integral multiple of NH upon 2 pi, where N is the orbit number, or you can say energy level. Yes, when that particular electron obeys this, then it will be allowed in that orbit. Until and unless, next point, until and unless the electron is revolving in its own orbit, it will neither radiate energy nor gain energy. Yes, it will neither lose energy nor gain energy. Therefore, they are also called energy levels, and they are sometimes also called stationary states. Why they are called stationary states? Because energy remains. It's not that electron remains fixed. Stationary, don't come to the conclusion that electron is fixed. No, electron is revolving. Why it is called stationary state? Because the energy of that orbit for that electron remains fixed. So in this manner, Bohr overcame the Rutherford's difficulty to account for the stability of the atom. Greater the distance of the energy level from the nucleus, more is the energy associated with it. As the distance of the energy level from the nucleus goes on increasing, the energy also goes on increasing. And these were numbered using which number? N, that is principal quantum number. N is equal to 1, first energy level, K shell. N is equal to 2, second energy level, L shell. N is equal to 3, third energy level, M shell. N is equal to 4, fourth energy level, N shell. Yes. Next point. Yes, ordinarily an electron continues to move in a particular stationary shell or an orbit, or you can say energy state. And such a state is called what? It is called ground state. Lower energy state is called ground state, and that is the stable state for that electron. When energy is given to the electron will gain or absorb energy, and it jumps from lower energy level to any higher energy level. And that higher energy level is called what? Excited state. And the process is called excitation. It is called excitation. And excited state is always unstable. So what that electron does, it will jump from, it will lose its energy, radiate its energy by jumping from higher energy level to lower energy level, that is excited state to its ground state, by radiating the energy. And that process is called transition. It is called what? It is called transition. Yes. So this is the postulates of Bohr's model of an atom. So this is all about the postulates of Bohr's atomic model. It is all about the postulates of Bohr's atomic model. Yes. So in the next class, we'll be discussing about what were the advantages of Bohr's atomic model, what were the advantages, and what were the disadvantages. Still, Bohr's model, with all these explanations also, Bohr's model was not accepted. So what was the disadvantage also we'll be discussing. Then if this also had some disadvantage, then which was the model which was accepted for atom. Today, what structure of atom we see, what was the model all about, that we'll be discussing in our next video. So for now, I hope you have understood the concepts. Yes, please do look after all the concepts what I've explained. In the next video, we'll be continuing with the next part. Thank you.